Hello again, everybody. Welcome back. First things first, thank you to everyone who's watched the first video, right? Honestly, the fact that even 10 people sat through me talking about Euclid's obsession with triangles, it's a miracle, right? Personally, it is. Now, I know the sound in that one was, let's call it abstract. I've tried to fix it in this one, but if the issue still persists, uh, we'll have to find some new fixes and find it soon. And just to be very clear, I'm no professor in mathematics, I'm no expert, I'm just a very curious person who really loves mathematics. And if you're here, maybe you do too, or at least you're open to the idea of falling in love with it. Right, then let's get into it. Last time we stopped at Euclid, right? But today we are shifting gears, right? We are moving to the 8th century. Now, 8th century in Europe, right? People were busy burning witches and mispronouncing Latin. But Baghdad became the mathematical capital of the world. This period was also known as the Islamic Golden Age, right? Now, there was a library that grew up during this time. It's called the Bayat al-Hikmah, right? And it was called the House of Wisdom. But it's not just a library, right? It was how do I put this? Maybe consider it the Hogwarts, right? But instead of potions, they probably were brewing algorithms. Now, and among the legends who sat in Bayat al-Hikmah, there was a man called Al-Khwarizmi. Al-Khwarizmi. His very name gave us algorithms, right? The word algorithm that we use, it has been derived from his name, and he wrote a book. The name is massive, really. I'll try to pronounce it. I've written it here somewhere. It's called Al-Kitab Al-Muqtasar Fi Hisab Al-Jabr Wal Muqabla, right? I'll probably try writing it. Al-Kitab Al-Muqtasar Fi Hisab Muqabla, right? Yeah, it's a huge name, I know. And please pardon my pronunciation. I'm trying my best here, please. Okay. This word algebra, the word algebra is derived from it. Algebra. This man gave us algebra, right? But what was algebra back then? Like, we'll have to think it from very intuitively, right? Because there were no symbols, there were no x's, there were no y's, no equal signs, nothing, right? It was very rhetoric in that sense, right? He would literally write a square and 10 roots, 10 roots equal 39. Now let's take a moment and think this through, right? What is it trying to say here, right? A square, so basically it's an x square, right? And 10 roots, right? So that is basically 10x. 39 is 39. So this basically is a mathematical equation, right? Now, but he did not have the algebraic tools to solve it, right? So what did he do? He solved it geometrically, right? He rather visualized it. He visualized it as a square, and he visualized it with some rectangles to complete a bigger square, right? I'll insert a tutorial which I've recorded to explain how he has done it. Welcome to the demo. Here we have an equation x squared plus 10x equal to 39. What this basically means is x squared plus 2 times of 5x equal to 39, right? Which basically means there's a square with side x, right, which is shown by the blue region, right? And we have two rectangles with side 5 and x, which is shown by the green region, attached to two ends of that square, right? Now this gives us a hollow region, right? That hollow region can be filled only by a square whose sides are 5 centimeter each. Therefore, the area of that yellow region will be 25 square units, right? Now, the entire area of this entire larger square will be 64 square units with side x plus 5. Now, x plus 5 side, if we have a square with side x plus 5, which gives us the total area of 64, which means x plus 5 must be 8, right? And that gives us, if x plus 5 is 8, then x must be equal to 3. Thank you. Right. I think you've already seen the tutorial. So as you can see, what he did is basically he completed the square. That's right. This is the technique that we still use, which we call completing the squares, right? Completing the squares. I'm pretty sure if you've done algebra, some bit of algebra in your mathematics in middle school and then high school, you know what completing these squares is, right? It's a technique we still teach today, right? And this man Al-Khwarizmi used it many centuries ago, right? That's how developed their mathematics was. He came up with this method algorithm, right? Without knowing nothing, right? He had no mathematical tools, numericals, no calculator, nothing. The only thing that he had was geometry in his toolkit. Now that's something, right? But the contributions of the Islamic age doesn't just end here, right? There are multiple people who have come after this, right? Who were there during this period. Even there was a man called Omar Khayyam, right? He solved cubic equations. Of course, he used geometry to solve them, but yeah, he gave us cubic equations. Then there was a man called Al-Biruni. He did something nobody could think of. He estimated Earth's radius with shocking accuracy, right? He estimated Earth's radius. And it's a fascinating story how he did it. We'll probably get into it later, right? Then there was a man called Al-Tusi. He started trigonometry as a standalone subject. But most importantly, their primarily most important contribution was they helped spread the Hindu-Arabic numerals. That we still use. Europe, well, they were still trying to figure out the Roman numerals, but unfortunately you can't do calculus that we do today using Roman numerals, right? But like all things, the golden age dimmed. Knowledge made its way back to Europe through Spain, through translation, and through trade. And by the 1600s, Europe's eyes were wide open. It was time for the Renaissance. And during Renaissance, maths was ready to grow as well. Now, I'm pretty sure you've heard of the name René Descartes, but it's okay if you haven't. He was a philosopher, he was a mathematician, and he was, let's just call a professional overthinker. He said, I think, therefore I am. But he also said something important. He said, let's use algebra to solve geometry. And that is how we came across the subject that we now know as coordinate geometry. You'll probably have to curse Descartes for introducing you to graphs, because without him, no graphs equal to no calculus equal to no physics equal to no engineering. Yeah, I mean, probably that man started it all. I don't know. Yeah, now let's move to the late 1600s. There were two men, right, worlds apart, and they were trying to solve this similar sort of a puzzle, right? The question was, how fast is something changing? Now that's an intriguing question, right? By the way, if you guys still haven't noticed, I'm focusing less on the mathematics part of it, things, rather the questions of it, right? I'm focusing on how these people came up with these solutions rather than what they came up with, right? Because I believe it's very important to inculcate these stories, because these are the stories that motivated me to study maths as a subject. I believe you guys will love it too. Right. Coming back to the topic. So I talked about two men, right? Who were these gentlemen, right? Uh, you've heard of them, I'm pretty sure. The first man is Isaac Newton, quite famous in his own right. And the other man, I'm pretty sure you've heard his name as well. It's Gottfried Leibniz. Now, Leibniz and their contribution was to the subject that we now know as calculus. Right? Leibniz gave us all the symbols that are associated with calculus. Right? He gave us the notations ddx, which we now know as differentiation. And he also gave us fx dx, which we now know as integration. So both of them were sort of asking similar questions, right? They were asking, what if we zoom into a curve infinitely close, right? That was the primary question that they were looking at. So what if we zoom into the curve infinitely close, right? Now try to visualize this, right? You have a curve, right? So because as I said that there was coordinate geometry had come in, so for an specific value of x, you have a certain equation that represents the value of y coordinate, right? And you have plot a graph on a curve, and you've got sort of a curve, right? That's the sort of thing that you've got, right? So for a particular value of x, there's a particular value of y, which is an f of x. This maybe is f of xy. And for a particular x1, this is our f of x1, right? Now that's the sort of intuition that we're looking at here, right? And he asks us, this man, is how fast is this particular curve growing, right? So that's the idea. Now, to better understand, for a better understanding, I have recorded a tutorial which I will add right somewhere in between, but till then I'd urge everybody to like sort of stick with me and start visualizing this, right? So and Newton sort of asked a similar sort of a question, but a little different, which is what happens to motion when time becomes infinitesimal, right? Because Newton was more associated with time, right? Leibniz was much more associated with general mathematics, but when we talk about Newton, he was much more focused on the motions of things, right? Physics part of it, right? Now, this that I'm talking about, right? This was not just maths, right? This was beginning of calculus, a very different branch of mathematics altogether, right? They invented ways to talk about instantaneous change, right? Instantaneous change. Now this is another word that will come across your high school mathematics quite a bit, right? Whenever you've read any form of calculus, some professor will come up with this term, instantaneous change. So what does this mean, right? It basically means is when the change is infinitesimally small, that's what they mean basically. It's and this basically gives us everything, right? How a curve bends, how speed varies, how light reflects, everything. Now Newton had a different word for it. He called it the fluxions, right? Whereas Leibniz called it differentials. Now we know it as differentials, and probably I'll refer to it as differentials only, but it's a good thing to know, right? Newton had a different name for it. He called it fluxions, right? Welcome to the demo. Imagine a function, say st equal to t square. This tells us the position of an object over time. Now pick 2 points, t1 and t2. The position associated with them is s of t1 and s of t2. Now if we have to find the average speed between these two time points, that is basically change in position divided by change in time, which we have represented here as delta s by delta t, which we'll call it as s of t1 minus s of t2 divided by t2 minus t1. Now, but what if we want to find how fast it's going exactly at t equal to 3? Well, we move t2 closer to t1, closer, until they merge. Suddenly you're no longer calculating average speed, you're finding the slope of the tangent line.
that slope will give you the instantaneous speed. That slope is calculus. This is exactly what Newton and Leibniz gave us. The instantaneous speed has been represented as ddt of s, and eventually we have calculated using standardized derivative formulas. We will get into it later maybe.
I hope you've enjoyed the tutorial. Now, as you've seen, this explained everything, right? It explained gravity. It helped us model epidemics. It helped build bridges, launch rockets, train AI. Calculus is everywhere. In all honesty, it's everywhere, right? But all of it, right from falling apples to flying spacecraft, started with a Persian librarian, a German philosopher, and a stubborn kid asking, "How fast?" right now.
See, in all honesty, I'm not here to teach you mathematics, the traditional mathematics at least, because you will find several teachers who are far better and much more qualified than me to teach you all those stuff. Rather, what I intend to do is to discuss mathematics with you from a purely story point of view, because I believe that's where the fun in mathematics lies. That's where this is the part that intrigued me to study that subject so much, and that is the thing that I want to impart to you guys.
Right, this is where I think we'll end our class today. If you've enjoyed this journey from algebra to calculus, thank you for sticking around. Really, thank you. And I hope you will continue sticking around, because next time we're probably taking a bold leap. We're leaving behind motion, gravity, and curves, and probably diving headfirst into infinity. Infinity, right? That's what we're looking at. We'll come across a man called George Cantor, right? George Cantor. What he did was he asked a very important question. Yeah, he asked, "Are all infinites the same size?" Now, this is a question that probably I'll leave you guys with, right? You guys can wonder the same, right? It's a good place to end the class, right? Uh, and what he perhaps will find out in the next video, that what he found out shook the very foundation of mathematics. He gave birth to set theory, and he kick-started modern mathematical logic, and opened doors to questions even your calculator would rather not answer. So next time we're talking about infinite, the unthinkable, and the beautiful madness that is modern mathematics. Until then, stay curious, stay kind. Thank you.